Picture training a very deep neural network in the early 2010s. You set your learning rate too high and the loss explodes. You initialize weights slightly wrong and gradients vanish into nothing. You use a sigmoid activation and the network simply refuses to learn. Practitioners had a whole bag of fragile tricks to keep training alive, and the deeper the network, the more fragile everything became. The paper we're talking about today, Batch Normalization by Sergey Ioffe and Christian Szegedy from Google, is the one that broke that fragility wide open and became one of the most cited contributions in deep learning history. The authors start with a deceptively simple observation. When you train a deep network with stochastic gradient descent, abbreviated SGD, every layer is essentially trying to learn a function whose input is the output of the layer below. But as training progresses, the parameters of those lower layers keep changing, which means the distribution of inputs that any given layer sees is a moving target. They give this phenomenon a name: internal covariate shift. Think of it like trying to learn to hit a baseball where the pitcher's mound keeps moving closer and farther between every pitch. Even if you're getting better at swinging, you're constantly recalibrating to a new distribution of incoming pitches. In a deep network, this problem compounds with depth because tiny shifts in early layers get amplified into huge distributional changes by the time they reach layer 50. This is especially painful for saturating nonlinearities like sigmoid or tanh. If the pre-activation of a sigmoid drifts far from zero, the gradient becomes essentially zero, and the unit stops learning. The community had largely worked around this by switching to ReLU activations, using careful initialization schemes, and keeping learning rates small. These workarounds help, but they treat symptoms rather than the underlying instability. Prior work had tried whitening activations, meaning transforming them to have zero mean, unit variance, and being decorrelated, either between training steps or by modifying the optimizer. But the authors point out a subtle and important failure mode in those approaches. If you normalize activations as a post-processing step that's separate from gradient descent, the gradient update doesn't know about the normalization. They give a concrete example. Imagine a layer that adds a learned bias and then has its mean subtracted afterward. Gradient descent will happily keep increasing the bias forever because the normalization cancels its effect on the loss. But the optimizer can't see that cancellation. The bias drifts to infinity while nothing actually changes. The fix has to make normalization a first-class citizen of the computation graph, something gradients flow through. Here's how batch normalization actually works. For each scalar feature going into a layer, during training, you look at the current mini-batch and compute the mean and variance of that feature across the batch. You subtract the mean and divide by the standard deviation with a tiny epsilon added under the square root for numerical stability. Now your feature has roughly zero mean and unit variance across the batch. But the authors realized that forcing every pre-activation into this narrow range could actually hurt the network's expressiveness. If you normalize the input to a sigmoid, you've trapped it in the roughly linear region around zero, and the network loses the ability to use the nonlinearity. So they add a clever twist: 2 learned parameters per feature called gamma and beta that scale and shift the normalized value. Crucially, if the network decides that the optimal thing to do is undo the normalization entirely, it can, by learning gamma equal to the standard deviation and beta equal to the mean. The transform can represent the identity, so capacity is preserved. The network gets to decide how much normalization it actually wants. 2 design choices deserve attention. First, they normalize each feature dimension independently rather than doing full whitening with a covariance matrix, because full whitening would be expensive and require regularization when the batch is smaller than the feature dimension. Second, they place the BN transform right before the nonlinearity, normalizing the pre-activation W times U plus B, rather than the layer input itself. The reasoning is that the pre-activation tends to have a more symmetric, roughly Gaussian distribution, while the input from the previous layer's nonlinearity might be sparse or skewed. They also note that the bias term becomes redundant since beta absorbs it. For convolutional layers, they extend the idea by normalizing jointly across the batch and across all spatial locations of a feature map, learning one gamma and beta per feature map, which respects the translation invariance that convolutions are built on. At inference time, you obviously can't depend on mini-batch statistics. So during training, they track running averages of the population, mean, and variance. And at inference, these fixed statistics turn BN into a simple, linear transform that can even be folded into the preceding weight matrix. This makes inference deterministic and cheap. Now the results are what made the deep learning community pay attention. On ImageNet, applied to the inception architecture, just adding batch normalization matched the original accuracy in less than half the training steps. With aggressive modifications enabled by BN, like raising the learning rate by 5 times, removing dropout, reducing weight decay, and accelerating learning rate decay, they hit the same accuracy 14 times faster. Cranking the learning rate up 30 times, they reached 74.8% top 1 accuracy, beating the original by a healthy margin. Perhaps most striking, they trained a sigmoid network on ImageNet to 69.8% accuracy. Without BN, sigmoid networks of this depth couldn't get above chance on this task. An ensemble of batch-normalized networks reached 4.9% top 5 validation error, exceeding the estimated accuracy of human raters on this benchmark for the first time. The authors also offer some intuition for why higher learning rates become safe. Batch normalization makes the network invariant to the scale of weights in a precise sense. Scaling a weight matrix by a constant doesn't change the BN output, and actually makes the gradient with respect to that weight smaller, which counteracts runaway parameter growth. They further conjecture, though they don't prove it rigorously, that BN pushes the Jacobians between layers to have singular values close to 1, which would mean gradients neither vanish nor explode as they propagate. And finally, because each example's normalization depends on which other examples happen to be in its mini-batch, BN injects a kind of stochastic noise into training, which acts as a regularizer and often makes dropout unnecessary. As for limitations, the method depends on having a reasonable mini-batch size. With batches that are too small, the mean and variance estimates become noisy and BN starts to hurt rather than help. There's also a train test discrepancy. During training, you use batch statistics. During inference, you use population statistics. And if these diverge significantly, you get a subtle distribution shift between training and deployment. The authors don't deeply explore recurrent networks, where applying BN across time steps is non-obvious and turns out to be genuinely tricky. And while the paper frames the entire story around internal covariate shift, later work has questioned whether reducing covariate shift is really the mechanism by which BN helps, suggesting instead that it smooths the optimization landscape. The intuition the authors offer is compelling, but the precise theoretical story is still being written. Now let's walk through some questions you might have after hearing all of this. First, why is the learned scale and shift, gamma, and beta actually necessary? Couldn't the next layer just learn to undo the normalization if it wanted to? The issue is that without gamma and beta, you're forcing the pre-activation of the nonlinearity into a fixed distribution right at the moment it matters most. For a sigmoid, that means trapping it in the linear regime. The next layer can scale the post-activation output, but it can't recover the saturation behavior that was destroyed by normalization. Gamma and beta sit precisely at the right point in the computation graph to restore the freedom the network needs while still letting normalization happen during the forward pass. Second, why normalize the pre-activation rather than the input to the layer? Because the input to a layer is typically the output of a previous nonlinearity, like ReLU, which produces a sparse, asymmetric distribution that's heavily shaped by training dynamics. Normalizing something that's half zeros doesn't give you a clean Gaussian-like signal. The pre-activation, which is a linear combination of many inputs, tends to be smoother and more symmetric by the central limit theorem, so normalizing it produces more stable behavior and more effectively prevents the downstream nonlinearity from saturating. Third, why does batch normalization act as a regularizer? Because at training time, the normalization a given example receives depends on which other examples happen to share its mini-batch. The same input image will produce slightly different normalized activations depending on its batch mates. This injects stochastic noise into the representations, much like Dropout does by randomly zeroing units. The network can't memorize exact activation values for individual examples because those values fluctuate batch to batch, which discourages overfitting. For large-scale recommendation systems, the ideas here translate quite directly. Ranking models for ads, feed ranking, or video recommendations are typically very deep networks consuming dense features mixed with sparse embeddings, and they're notoriously sensitive to feature scale, initialization, and learning rate. Batch normalization, or its descendants like layer normalization, has become standard practice in these towers, allowing teams to train much deeper architectures with aggressive learning rates and dramatically shorter wall clock training times, which matters enormously when you're retraining models daily on freshly minted user interaction data. The deterministic linear transform inference behavior is also very friendly for serving, since BN can be folded into the preceding weight matrix at compile time and adds zero serving latency. That said, there's a subtle but important production consideration. Recommendation systems often have severe distribution shift between training data and live traffic due to feedback loops, seasonality, or new content. The population statistics that BN freezes at training time can become stale, leading to silent quality regressions. Some teams address this by recomputing BN statistics on recent traffic before deployment, or by switching to layer normalization, which doesn't depend on batch statistics at all, an approach that's become more common in the transformer-based retrieval and ranking architectures now powering many large-scale recommender stacks.